Hello, my name is Maxim Aran. I'm going to talk about how we use tensors for anomaly detection. This is a project I worked with Justin Moore and Boyan Alexandrov at Los Alamos National Laboratory this summer. Malicious users such as compromised accounts or insider threats continue to be a big problem for organizations. 80% of the breaches result from stolen credentials, and 57% of data breaches involve insider threats. And cost of malicious insider increased by 15% in recent years, and most can go unnoticed for a long time, according to the reports. We can exploit the large-scale collection of user authentication data to detect anomalies by training a model of known user behaviors and detect the ones that deviate from the norm. Let's take a look at Lano. With nearly 12,000 users and 15,000 network machines, can generate an average of 3.5 million daily user authentication events alone. And we can exploit this data to train the model. To this extent, there have been significant work previously in detecting anomalies using non-negative matrix factorization. And we expand upon previous work by exploring the multidimensional problems created by the user authentication events. Let's take a look at this diagram. Consider the figure representing logging into their destination device from the source devices. This is authentication event demonstration. And let's say user one uses this source computer to log on to these destination devices normally, and same for user two for its machines. And we have a malicious actor, Eve. Let's say Eve, acting as user two, logs on to destination device three, user two's destination device. Now, this should be detected as an anomaly because it's a lower probability of event happening, because destination device 3 was never logged on from source device 3. Consider another example if Eve, acting as user 2, logs on to destination device 2. Not only destination device 2 was never logged on from source device 3, user 2 never logged on to that device, in this case Eve acting as user 2, so it should be even lower probability and detected as an anomaly. In this figure, what you see here is an anonymized LAN user authentication, hourly authentication events over 90 days. It clearly can be seen this user's pattern of activity at work hours and work days. And this is an example of easily predictable user behavior. And that's what we want to do. In this project, we use the dataset unified host and network dataset that consists of NetFlow logs and host event logs collected at LANL over 90 days. There's a red team activity between days 57 and 82, which can be used as ground truth in anomaly detection. We extract the attributes user, which initiates an authentication event, source device, where the authentication originates, destination device, which user is authenticating to, hour of the day and day of the week attributes, and status representing fail or success of the logon activity. With these attributes, we can generate three tensors, with one of them dimensions user, source, destination, and status. And then we can add an hour dimension, which is hour of the day, and a day dimension, day of the week, going all the way with a tensor with 6 dimensions. This will result in tensors that are very sparse. For example, if you look at the tensor with dimension user, source, destination, status, it will has 1.63 times 10 to the power of 12 values in total, but only 166,000 of them will be non-zero. We can use this as in our advantage. First of all, we don't need to store the dense format of the tensor in the memory. We'll just use the coordinates of non-zero values as a sparse representation. And this will also give us a fast runtime, since Poisson distribution only need the non-zero values, occurred events, to calculate the likelihood. In this analysis, we use canonical polyodic Poisson distribution decomposition by Tamara Kolda. There's a CP-APR algorithm where the original tensor is approximated by Poisson distribution, And as a reminder, CP decomposition is where the original tensor is approximated by sum of rank 1 tensors, and each rank 1 tensor is a component build up of the dimensions. Here we call it factors of the original tensor, and it is the outer product of these factors. And we have the lambda value that takes in the weight of this component. And we'll make use of the log likelihood to find the rank that best describes the latent space of the original tensor. We will choose the rank by taking the decomposition of the validation training set over different ranks, and then choose the one that gives the highest log likelihood. And we'll also apply smoothing to reduce the false positive rate. We'll use the rank 1 tensor decomposition and weight its Poisson lambda parameter with 0.1, and we'll add the best rank R and take its decomposition, and will weight its lambda with 0.9, and that will allow us to keep the prediction characteristics. And as a reminder, Poisson distribution is in statistics is a probability distribution of randomly occurring count of events over a timeline. For anomaly detection, we'll calculate the p-value of each event by multiplying the indexes and the factors with the weight and sum it over R, and use that lambda with the CDF, Poisson CDF, to get the p-value, and lower p-value will indicate anomalous activity. If you look at this diagram, as we add more, this is p-values of the red team activities. As we add more dimensions, the p-value remain closer to 0. And this is probably happening because anomaly detection is becoming easier or more sensitive as we add hourly and daily activities as well. If you look at the ROC curve here of our results, we are able to detect up to 0.993 AUC score, and precision recall is overall low for each of the 3 tensors. That is because we have a very high class imbalance. For example, with p-value threshold of 0.001, we can detect almost all 108 out of 138 anomalies, but it will falsely classify 3.5 thousand out of 3.5 million. And for tensor with 4 dimensions, we're able to take 56. It will have less false positive rate of 104. If you look at this table here for the p-value statistics, it can be seen that average p-value for red team drops as we add more dimensions, because the tensor becomes more sensitive to the temporal dimensions, and the benign one actually increases, which is what we want. The other thing we did was fusing the p-values over the rest of the dimensions of the tensor to predict the other dimensions, and this allows us to compare the previous results where matrix factorization was used. For example, if we want to predict to user source, we will fuse the rest. For this one, for example, destination and status, and this one, destination hour and status. And when we do that, for example, for user source, we are able to achieve a UC score of 0.9939 and user destination 0.9379. And this is actually higher than the previous findings, where a UC score for user destination was about 0.9090, and for user source was 0.9379. With that, thank you very much for your time and for watching my presentation.